Hey guys, this is Mr. Gran with our lesson on trig word problems. So trig problems that have words in them. Alright, so some of the things we're going to be doing, a lot of this is going to be based on setting up a diagram, so drawing a picture of the right triangle and getting the numbers in the right spots. Then your standard solving missing angles and missing sides, and then also kind of a special case for word problems, angles of elevation and depression. So we'll learn about what those are. All right, so word problems, keywords are going to be very important here. So add this to your notes, screenshot this so that you can use this as you're practicing these word problems. So there's always going to be keywords that you should look out for in these problems that give you a hint as to where the number should go, right? So some numbers or some words that I've gathered here are things like anything that lets you know something that is vertical, that would be your vertical side, right? So wall, height, vertical, tree, pole, cliff, altitude, like the altitude of an airplane. All of those would tell you that it is this side of your triangle. Horizontal is sometimes a little more ambiguous. Ground is always going to be here. Shadow, it always lays on the ground, so it's always flat on the ground. Then some words like from and far, most of the time are going to tell you that it is the horizontal side rather than the vertical or the diagonal side. For hypotenuse is going to be almost always some physical object like a kite string, like a wire, a ladder, right? A ladder, when you lean a ladder up against a wall, you lean it at an angle, maybe not as sharp as this one, but it's not straight up and down and it's not horizontal. A ramp or a line, like a zip line specifically. All right, so the steps that I'm going to use when I do these. First off, I'm going to highlight the two sides and angle on the problem. Each of these problems has two sides and one angle. Two things are going to have a number and then one thing you're looking for. So you're either given one side, an angle, and looking for the other side, or you're given two sides and looking for the angle. Then we're going to draw the triangle, place our numbers and the X on the appropriate spots. We'll label our sides opposite, adjacent, hypotenuse. Then we will make our decision. Are we going to use sine, cosine, or tangent? And then we'll set up and solve. All right, so taking a look at this first one. 12-foot ladder is leaned up against a wall. The base is 5 feet from the wall. What angle is formed by the ladder and the ground? All right, so we've got our important information here. 12-foot ladder. The base of the ladder is 5 feet from the wall. And we want to know what is the angle formed by the ladder and the ground. So when I set this up, I can start out with just sort of a generic right triangle. And just to highlight, a ladder, right? This is my ladder leaning up against the wall. Obviously not to scale, that's not super important though. Okay, so we've got a 12-foot ladder. That is that part. The base is 5 feet from the wall. From was our horizontal keyword. And then what is the angle formed by the ladder and the ground? So that's what it's asking us to find, is the angle, and it's the angle formed by the ladder and the ground. Well, here is the ladder, here is the ground, so the angle where those two things meet is where I'm going to put my X. Okay, opposite, adjacent, hypotenuse. So the right angle points at the hypotenuse. If the angle I'm using is in the left side, the opposite of left is right, so the side on the right is opposite, and the other one is adjacent. All right, in this case, no information on the opposite. I'm just using A and H, so that is going to be a cosine problem. All right, when I set this up, cosine of X is equal to adjacent over hypotenuse. Now with inverse trig, or with finding a missing angle, remember we're using inverse trig, So I get rid of cosine on one side by doing inverse cosine of both sides, like that. All right, now let's go to our calculator. Make sure you're in degree mode. We'll do second cosine 5 divided by 12, and we'll call that 65.4. All right, here's another one. A guide wire supports a telephone pole. The wire attaches to the pole 25 feet in the air. The wire connects to the ground 12 feet from the base of the pole. And what is the angle formed by the wire and the pole? All right, so for this one, set up just a generic looking right triangle again. All right, so it says the wire attaches to the pole 25 feet in the air. That is a vertical measurement. Then the wire connects to the ground 12 feet from the base of the pole, 12 feet from, that's our horizontal measurement. And what is the angle formed by the wire and the pole? Well, the wire is here, the diagonal. The pole is the vertical. Where those two things meet, that's where I'm going to put my x. That's the angle. All right. The right angle points to the hypotenuse, so this is my h. Now my angle is in the top. The opposite of top is the bottom, so that is my opposite, and 25 is my adjacent. Don't need the hypotenuse for this. TOA uses opposite and adjacent, so this is a tangent problem. So tangent x is equal to opposite over adjacent. And now to solve this, I'm going to use inverse tangent. So go to my calculator, second tangent, and about 25.6. All right, moving on. We're flying a kite, gets stuck at the top of a tree. We let out all 100 feet of string for the kite. The angle the string makes with the ground is 75 degrees. And instead of worrying about how we get our kite back, we're wondering how tall is that tree? All right, so let's make a happy little tree here as part of this problem. We'll say that that's a tree. And we've got a kite stuck up in the top of it. And that kite is attached to a string, and that's going to make our right triangle. Okay. Now, we let out 100 feet of string. The string connecting to the kite was the hypotenuse. The angle the string makes with the ground, so here's the string, here's the ground. I'll put my x right there. And we're wondering how tall is the tree. Oops. That should be a 75, not an x. That's where the x is. How tall is the tree? Okay. 100's our hypotenuse. If the angle's in the left side, the opposite of left is right. And that means there's my adjacent, which we don't really need for this. So this is going to be a SO problem. Now this one's not going to be inverse trig like the other ones. So if you have my class, I like to do my ratios like that. Sine of 75 over 1 when I'm solving for a side rather than an angle. And it's opposite over hypotenuse. And the reason I like to put it over 1 like that is then it sets up nicely for cross multiplication. Now on one side I have x times 1, so that's just x. And then the other side is 100 times sine of 75. So let's plug that in. 100 sine 75, and about 96.6 feet tall. So pretty good sized tree. All right, let's talk about angles of elevation and depression. So with an angle of elevation or depression, I'm going to show both scenarios and then give you a shortcut for this. So let's say that I'm standing down on the ground and I'm looking out at the base of a cliff. So I'm looking out horizontally, right? Now I elevate my line of sight upward. What that does is creates a right triangle where this angle is the angle of elevation, the angle that moved my line of sight from horizontal and elevated it up vertically. Now let's say my buddy is standing on top of the cliff that I looked up at, and he's looking straight out, and now he lowers or depresses his line of sight to look down to me. What that does is creates another right triangle, a very similar right triangle, and the angle here is the angle of depression. Now what's special about angles of elevation and depression is this. If you notice, for both of these, there's some similar things here. The hypotenuse is always the diagonal again, but if I pay attention to the opposite and the adjacent, I've got a vertical side for both of these. And for both of these, the vertical is the opposite. I also have a horizontal for both of these. And for both of these, the horizontal is the adjacent. So no matter how you set your triangle up, it actually turns out it doesn't matter if you use this diagram or this diagram and just put whichever you have, elevation of depression or elevation, in this corner, in the corner that makes it so that the opposite side is vertical and the adjacent side is horizontal. So a lot of times what teachers will teach with this is that whether you get elevation or depression, you just use one triangle and you always put the angle in this corner. And that way that vertical side is always the opposite, which is correct, and the horizontal is always the adjacent. A lot of times what students will do with this is they'll if they get an angle of elevation, they'll use this one, but they'll use this triangle and they'll try to say that the angle of depression is up here because they're imagining somebody up here, looking downward and forming this angle. But really, if you're going to put the only way that the angle of depression is in the top of the triangle is if it's this upside down triangle. Because if I put the angle here, now my opposite is on the bottom, and that doesn't work. Then your triangle is set up backwards. All right, so let's take a look at a couple of these. We've got a 30-foot tall flagpole, casts a shadow that's 15 feet long, and we want to find the angle of elevation to the sun. So here's our flagpole. Throw a little flag on top of that. And there's our triangle. The flagpole we know is 30 feet tall, so that's our vertical. The shadow's 15 feet long. We want to know the angle of elevation, and that goes right there, so that my opposite side is the vertical, my adjacent side is the horizontal, and hypotenuse I'm not using in this one, so I'm going to leave it blank. All right, this is a TOA problem. So tangent of our angle x is opposite over adjacent, so 30 over 15. Let's go to our calculator. Second tangent, 30 divided by 15, and 63.43. So we'll say, oh, I guess I can show my work here. So x is equal to inverse tangent of 30 over 15. And that was, what was it? 63.4, we'll say. All right, angle of depression one. Let's take a look at this. So our airplane is flying at an altitude of 2,500 feet. The angle of depression to the airport is 5 degrees. What is the horizontal distance to the airport? So I'm going to do this one with the upside down triangle. So if I've got airplane here flying, it's flying on a horizontal line. It has an altitude of 2,500 feet. Now, sometimes students want to put that number over here because this is where the plane is, but remember, like, the altitude is just the vertical measurement, so it can go over here. That's fine. The height over here is presumably the same height as over here, above the ground. All right, angle of depression to the airport is 5 degrees. And we want to know the horizontal distance to the airport. Now again, some students want to measure that along the ground, but it doesn't really matter. The distance from here to here, like if we made a line straight down, this distance is the same as this distance. So we'll put our x up here instead. All right, opposite adjacent hypotenuse. Hypotenuse is over here, no info there, so I'm gonna leave it blank. Angle is up in the left corner, so the opposite of left is right. And then x is our adjacent, another tangent problem, TOA. So tangent, I might need a little more room. Tangent of 5 degrees over 1, because we're finding a missing side, is opposite over adjacent. Now we can cross multiply. So in this case, I've got x times tangent of 5 is equal to 2,500 times 1. Now to isolate x, I'm going to divide both sides by tangent of 5. That'll cancel out tangent 5 there, and I get that x is whatever 2,500 divided by tangent of 5 is. So let's go to our calculator. 2,500 divided by tangent 5, and that is my horizontal distance, 28,575 feet. All right, last one. Okay, we'll do this one with the not upside down triangle. So we've got a zip line carrying us 500 horizontal feet at an angle of depression of 12 degrees. Find the length of the zip line. Let's highlight some stuff. So 500 horizontal feet, angle of depression is 12, and we want to find the length of the zip line. All right, so there's my triangle. Hanging on to a little zip line right here. 500 horizontal feet is going to be on the ground. Angle of depression is 12 degrees. Now, a lot of people would make the mistake of putting the 12 degrees up here because they're thinking it has to be in the top if you have an angle of depression, but it's the same as here. That way, this will be my adjacent and the vertical will be my opposite. So I'm going to put it right there. And we want to find the length of the zip line. The zip line is the hypotenuse. All right. Sides. Hypotenuse is not an O. Opposite, adjacent. Don't need opposite. This is going to be a cosine problem. So cosine of 12 over 1 is adjacent over hypotenuse. And we'll cross multiply. X times cosine of 12 is equal to 500. Then we can divide both sides by cosine 12, like that. And x is going to be whatever number 500 divided by cosine of 12 is. So 500 divided by cosine of 12, about 511 feet, we'll say. All right. Hopefully you found that helpful. If you have any questions, let your teacher know, and have a great day.